Hello, this is Alan Volmsby here in Hawaii. December 11th, 2019. Live streaming on YouTube about physics, theoretical physics. And today I'll talk about the pear shape of barium. That's an element, a metal, and the pear shape of a nucleus is the protons and neutrons. An experiment was done by a large number of authors, and I'm going to compare that to my theory, and other people have theories also about the shape of the nucleus. So as you see in your picture is a small model of a nucleus that's kind of pear-shaped, and this is platinum model, but it's also shaped very similar to the barium. So here's a picture of the planning for barium on my periodic table, and it's like cesium and xenon. Let's see if I can focus on this. Oh, there's krypton and xenon 132, and the experimenters have found a pear shape. And you see how this has kind of a pear shape too. Now, I'm going to go back to that photograph and just turn this around for you a little bit here. Okay, so this one represents platinum, like I was saying, and it's has a large pyramid on top and small pyramids on the bottom of a cube, and it has armoring against collisions, and this pear shape has survival characteristics to it, and the experiments showed a pear shape, and they have theories that expected more of a round shape or a elongated elliptical shape, and sometimes pear shape, but the experiment showed quite prominent pear shape to it. So now the paper on the barium is copyrighted, so I'm not going to be able to show it to you. But you can go to it on the internet, and I'm looking at it right now. It's at phys.org. And, oops, pardon me. So the title of the article here from 2016 was Heavy Barium Nuclei Prefer a Pear Shape. And I think it's legal for me to read parts of it to you here. And heavy barium nuclei up to, they're looking at barium 144. And normally it's 132 is the number of protons and neutrons. So this has abundant neutrons added to it during a beam. Now, the experiment was done with Argonne National Laboratory. It was scientists from the US, UK, and France. Mr. Boucher was involved with that. And let's see how you spell his name here. Oh, there it is. Experiment by B. Boucher et al. I believe there's about 70 authors, like in a previous paper I was talking about. And that was from March 17, 2016 in Physical Review Letters. The name of the article by Boucher was Direct Evidence of Octupole Deformation in Neutron-Rich 144 Barium. So barium is element number 53, I think. Let me look at my chart here. Oh, 56. Yeah, barium 56 and mass number 144. So the question is, why is it deformed? So I proposed this theory independently of the experiment, before I even found out about the pear-shaped nuclei, I had proposed a theory of the pear-shaped barium and other elements. And it's all about the survival of the nucleus. Regardless of when barium was created, whether it was in a Big Bang or in the center of a star or anything primordial, it has survived until this day, in my theory, with a static shape. This is a static nucleus theory, and this means that the protons and neutrons are in fixed positions for a very long time. And the pear shape is because it's a dart shape. In other words, the dart has a front end and a tail end. And the pear, the big end is the front, and the small end is the back on the pear-shaped nucleus. And this is armoring that ensures survival. It's a hexagonal close pack of protons and neutrons on the outer surface of the nucleus. And as you can see in here on the left, cesium here, you see has the red cubic lattice with the large gaps between them, and then on the top it has the hexagonal close pack lattice with the very small gaps, and so that's less vulnerable. So these facts is what helps it be surviving so well. Now, there's two ways a nucleus can be synthesized, either a unidirectional blast synthesis or in a stellar uniform collisions, like in the sun or something where the collisions are coming from all directions to form a new element, a new nucleus. Or like in barium, I proposed that it was a blast coming from one end. Of course, a collider, any kind of Argonne National Laboratory using the caribou source of the californium nuclei, and then you accelerate it using the Atlas accelerator to an energy carefully tuned to study nuclear excitations via electromagnetic interactions. So this kind of article would be nice to look at, but I can't show it to you right now. But I can show you the model that I made of a pear-shaped nucleus here. I'm going to turn it around for you. All right, so you can see that it's complicated, much more complicated than a pear. Now, that's because it's a hexagonal close pack on top of a cube. Face armored cubic lattice has the HCP surface, hexagonal close pack, and that makes it survivable. And the cube apparently is either primordial from a vast cubic neutron star, or it is easy to create cubes in stars just from neutrons and protons. The cubes assemble themselves somehow inside the sun. I prefer the primordial idea. Now, you could also use Blender 3D. I'm going to show you how to do that. I think I'll just turn my camera here while you're reading up on this slide here. All right, good. I have my camera pointed at the computer screen, and on Thingiverse, you could get these types of pictures. Let me show you where that is also. All right, we're over on the Thingiverse, and over here on the website, you could look up and down here at various nuclei, and you notice a lot of them are pear-shaped. We have polonium in the middle there. Oh yes, pear-shaped. And then above that, let's see, we have radon, also pear-shaped. And let's see, argon, thorium. Thorium is pear-shaped also. And the reason these heavy elements have so many pear-shaped elements in my proposed theory is that they were created in a blast. There was a unidirectional event where collisions were occurring from one side, and these are the survivors. These are the fossils from a primordial blast. And that pyramid on the top there is armor. It's called face armored cubic. That hexagonal close pack is protecting the cube. So let's go look at the cube now. There, you can see some simple cubic cores, and I've downloaded them now from this website here on Thingiverse.com, and I put them into Blender. And I'll just zoom back off here. All right, now I'm going to make barium for you here with Blender. So that's how easy it is. So, you know, we're going to be looking at the planning for barium because it looks like this. As we know, there's 5 layers, like cesium on the left there, 5 layers on the top pyramid, and then a smaller one with 4, and then a 3-layer cube. So we're going to put that together right here. Now I have to move that around left and right, up and down a bit here to make it all line up. Okay, we got that almost lined up. Now, on the sides, let's look at the planning again. We see on the left and right sides, we have these small pyramids of lithium-5. So these are little pyramids with 3 protons and 2 neutrons. And then that goes on the cube on all 4 sides. And on the bottom, we'll have a small pyramid put on there. All right, now I'm going to assemble this slowly and tediously for you on live streaming video because it's just so easy to do on camera. On the other hand, we could just use our imaginations that imagine I had just finished this up and then it looks much like the models which I was showing you of other things. Yeah, that would be easier than actually finishing all that CAD work there on screen for you. So I'm going to go to a little camera work here. And this is very green outside here in Hawaii. December 11th, it's about 80 degrees outside. Now barium has a nuclear structure which is very important because it has the charge distribution is now known. We have a new theory which I proposed and which you can believe in or reject and compare it next to other theories. For example, you could go to copyrighted books on, for example, modern particle physics. I bought this one. Let's see, the author is Mark Thompson. And under modern particle physics, they don't tell you about nuclear structure. Period. All right, now under another book that I got, it's copyrighted, so I can't really show you what's inside. As far as I know, it's legal for me to show you the front cover. Nuclear magnetic resonance spectroscopy. Let's see, this was by, I read this, by Harold Gunther. All right, it's a very thick book. It has a lot of, it's like 600 pages. I put in my own periodic table, but nuclear magnetic resonance spectroscopy knows almost nothing about nuclear structure, and they have lumped functional models of magnetic resonance and things like that, but they don't know what the charge distribution is, like I have proposed, that protons form lines of protons, and that there's a reason why, for example, carbon-13 is good for nuclear magnetic resonance, and carbon-12 is not useful for it. And these extended molecules, the nuclei, like barium, also have unusual properties that make it special to measure. But I find that something is useful, instead of those two books for nuclear structure, is just fluid dynamics. So, I can't show you what's in this one either. It's by Peter S. Bernard, and the strong nuclear force is involved in that. Now, as far as the other books that I have, this one is about orbitals. Now, the nucleus is connected directly to the orbitals and the spectrum. This is Orbitals with Applications in Atomic Spectra by Charles S. McCaw. And I'm sure once they find out that the charge distribution is now understood according to a theory in great detail, complete detail, then they can get the new calculations going for chemistry and atomic spectra. So another book here mentions nuclei and how useful relativistic hydrodynamics would be at cosmic scales or at tiny scales inside of the nucleus. But they don't really go into that much. They know nothing of nuclear structure in relativistic hydrodynamics, but they say it would be useful for nuclear calculations. Let's see, The Chemical Bond. I have been reading this quite a bit. 2 volumes, $240. Let's see, by Guerneau, Friedking, and Sasson Sheikh. So in this book, they talk about many different types of elements and the nucleus and how the shape of the nucleus is roughly spherical. I believe is the best approximation they have. Don't quote them on that. Maybe it was a different book that said that. Sorry. Let's see. Here's his book on fusion by Gary McCracken and Peter Stott. I think they have pictures of little nuclei in here that I can't show you. but they're very primitive, like as if they were drawn from 1940 or something with pencils. And you should go to like the internet and look up images on one of those search engines and find the silhouette of barium, or the barium structure, nuclear structure. And what you'll find is ancient pencil sketches, almost all spherical nuclei. Plasma physics, controlled fusion. You would think that nuclear structure would be important to them, but they don't know anything about it really. Is it pear-shaped or is it not? They don't even guess. Do they have a periodic table of nuclear structure that is even proposed? No. But I am providing that. All right, so now here we are in 2019, and we have the latest literature is available for everyone. This one is on spintronics. Let's see, Spintronics for Next Generation Innovative Devices by Katsuaki Sato and Eiji Saito. And they talk about a cosmology of the materials in solid state, tiny universes in a way. And so I think that science is ready for these new ideas, and I'm going to be continuing 3 days a week presenting these new ideas with the goal of creating the generator. And once the detailed charge distribution is accepted by standard scientists, then I'm assembling a team to produce the next generation of generator for clean electricity. I'm going to go over to the control panel now. Hey, and I have arrived back to tell you about barium. So I'm going to just pause for a drink here for a second. Ah, yes, that was good. Great, I found my glasses over here now. And I'm going to be winding down the production pretty soon, so mellow out. It's almost over. Okay, so I showed you the Blender 3D, and this can be used for archiving of these files for future generations. Also for future research on the hydrodynamics of the strong nuclear force. This Blender model provides boundary conditions for such simulations, and Blender also has physics built in. For example, smoke visualization could be used to show how space moves into the nucleus and time comes out for the strong nuclear force. And also collisions could be modeled, showing how thorium is more vulnerable to fission than radium is, for example. Now, I do have some links to tell you about here to get more details. ferronuclear.blogspot.com and pyramidalcube.blogspot.com or impuremath.wordpress.com. My name is Alan Folmsby. I'm here at 10 a.m. Hawaii time, Monday, Wednesday, and Friday. Thank you very much. Bye.